In this section we will have a closer look at the mobility procedures defined inside the LTE system. This means how the subscriber moves from one cell to another. This slide illustrates in a very simplified way the procedures for a handover from a UI between two base stations, a source eNode B or base station and a target eNode B or base station. Also the X2 interface between the two base stations is involved in this case. The mobility management entity is not changed. That means both base stations stay connected with the same mobility management entity or MME, so we have the case of an intra-MME handover. The MME is part of the Evolved Packet Core EPC in this figure. First of all, the UI is reporting measurements. This means neighbor cell measurements according to the measurement configuration provided by the base station. And the base station is then evaluating the measurement reports. The base station will decide about a handover in case, for example, a neighboring cell shows much better quality than the source cell. So this would be the handover decision. In case this neighboring cell belongs to another base station, we have an inter-base station handover, and the source base station will then communicate with the target via the X2 interface. The source will request a handover so that the target can do admission control and check whether it can accept the new terminal. In case it can accept the handover, it will send a handover request acknowledge message via the X2 interface. The target base station can then start the handover over the air interface. It is then sending the handover command to the UI, and in case of LTE, this is actually an RC connection reconfiguration message. It contains all the required information regarding the target cell so that the UI is able to access the target cell. The UI can then detach from the source cell and synchronize to the target cell. And on the base station side, data packets, sequence number information can be forwarded from the source to the target base station again over the X2 interface, and the target can buff the new packets. As soon as the UI is connected then to the target base station, the RC connection reconfiguration procedure is complete. And the paths between the Evolved Packet Core and the base stations can be switched so that the data path now goes to the new base station and all the new packets are delivered to the new target base station. So all the contacts, the UI contacts in the source base station can now be released, all buffers can be flushed, and all the resources can be released there. So there's not only intra-LTE mobility, but also LTE between 2G and 3G networks defined in the LTE. On this side, for example, the possible transitions between the LTE and GSM GPRS states, as well between LTE and wideband CDMA HSPA states are shown. In LTE there's only two protocol states defined on the radio resource control RRC level, the RRC connected and the RRC idle. These are shown in yellow here. And the mobility in RRC idle between LTE and the other technologies is done via cell reselection mechanisms. Mobility in RRC connected is done via handover procedures. For example, from the EUTRA RRC connected state to the UMTS cell DCH state. Or from the EUTRA RRC connected state to either the GSM connected or the GPRS packet transferred mode state. In between LTE and GSM GPRS, you can see that also cell change order mechanisms, abbreviated CCO, are defined, also including network assisted cell change, NACC. Of course, not only transition from LTE to GSM Edge and wideband CDMA HSPA, but also between LTE and CDMA 2000 based technologies is required. And this is true for both the HRPD high rate packet data and for 1x RTT circuit switched services. And this figure again shows the allowed state transitions in terms of state transition between RRC connected and the CDMA states and RRC idle and the CDMA states. Note that CDMA 2000 messages are sent transparently to the UI over the EUTRAN and the base station and the MME acting as relay points. All the described mobility scenarios we have just seen for 2G, 3G, wideband CDMA, GSM and CDMA are part of 3GPP Release 8 specifications. So these interworking scenarios, mobility scenarios, they are all part of LTE from the beginning. Now the next section will cover MIMO multi-antenna technology. MIMO is a key feature of the LTE air interface because it is needed to achieve the high throughput and data rate requirements for LTE. MIMO stands for multiple input, multiple output, because multiple transmit antennas are used that form multiple inputs to the radio channel, and typically multiple receive antennas are used, which are provided with multiple outputs from the radio channel. So a brief introduction to MIMO in general before we go to the LTE specific things. We've seen that MIMO basically means using multiple antennas at both transmitter and receiver side, but what are you doing with these multiple antennas? What are the gains to exploit? First of all, a diversity gain can be exploited. This is illustrated in the first figure shown here. By transmitting the same data streams over multiple transmit antennas, for example at a base station site, the receiver, which could be the wireless terminal, has multiple replicas of the same signal available. And so at the receiver side you can achieve a higher signal-to-noise ratio. This diversity gain is very efficient to combat fading over the mobile radio channel. However, the data rate cannot be increased because each antenna is actually transmitting the same information stream. You have actually more redundancy available. Note that typically the streams transmitted by each antenna are coded with an additional antenna-specific pattern to further increase the diversity effect. An example would be the space-time or space-frequency coding according to LMUTI. That is a very commonly used scheme. The next figure shows a slight difference, and it shows a simplified example for spatial multiplexing. And in this case, a multiplexing gain can be exploited by using the multiple antennas. And now each transmit antenna transmits a different data stream, S1, S2, and so on as shown here. And these streams are transmitted simultaneously over the same radio resources over the air interface. And this is possible by exploiting the spatial dimension. So by doing so, the data rate can of course be increased because now more data is actually transmitted over the resources at a certain point in time. However, of course, no diversity gain can be exploited. The transmission may not always be successful, and this really largely depends on the correlation characteristics of the mobile radio channel. If the channels that are formed between the transmit and receive antennas are highly correlated, then the performance of spatial multiplexing will deteriorate. So spatial multiplexing really works best in uncorrelated scenarios. And we really have a high dependency of the performance depending on the channel conditions, which is also the reason why spatial multiplexing typically is being tested in fading scenarios, and fading simulation is a very important testing feature for testing MIMO systems. In fact, it is also possible to switch between the MIMO modes, transmit diversity and spatial multiplexing, and this is also done in LTE. The decision which MIMO mode to apply is taken in the base station based on the UE feedback received. So MIMO is typically operated as a closed loop scheme using this UE feedback loop. Now, not to forget a third possibility of using multiple antennas. In the case of beamforming, an antenna array with closely spaced antenna elements is used to focus the energy in the direction of the terminal, and ideally also to null out interferers. This is achieved by adapting the amplitude and gains of each antenna element to form the beam. Beamforming is also supported in LTE, and it is especially beneficial for TD-LTE, the TDD mode, because of the reciprocity of uplink and downlink channels in TDD operation. This means that the uplink transmission from the mobile can be evaluated by the base station, and the necessary adaptations on the beam pattern in the downlink can be derived from this uplink transmission. Now this slide summarizes the MIMO modes used in the LTE downlink before we go in more detail on some of them. Transmit diversity is one MIMO mode. It is using a space frequency block coding scheme, SFBC, and that is used as an additional antenna coding. As explained on the slide before, the transmit diversity mode is increasing the robustness of the transmission, but not the data rate. So the space frequency block coding scheme will also be further explained in the following to give you an impression of what's really done there with the signal. Achieving the high data rates in LTE is possible by using the spatial multiplexing MIMO mode. Again, this allows transmission of different data streams simultaneously over multiple spatial layers. And to further improve the performance of this MIMO mode, a so-called codebook-based precoding approach is applied. That means the signal is pre-coded before transmission in an appropriate way. And this will be illustrated further in the following as well. There's an open loop mode and a closed loop mode available for this spatial multiplexing scheme. The closed loop mode is relying on UE feedback, and the open loop mode is beneficial at high mobile speeds where the UE feedback may not be reliable anyway. So then the base station can operate in open loop mode. An additional scheme used in LTE is called cyclic delay diversity. It is used in addition to spatial multiplexing as a further enhancement. An antenna-specific delay is added to the signal transmitted by each antenna, delaying the signal effectively, and this is done by a cyclic shift of the signal on each antenna. And this effectively results in an artificial multipath situation experienced at the receiver side, causing increased frequency diversity effect. Finally, beamforming can also be applied in LTE as well, which is especially relevant for the TD-LTE part. This picture illustrates the LTE downlink transmitter chain inside the base station. It shows the processing that is done for each code word that is output from the channel coding stage and what happens to it until the transmission over the antenna ports at the right-hand side. So what is a code word? A code word is basically corresponding to a transport block. The transport blocks pass down from MAC layer to the for transmission over the physical layer. And the code word is an entity that has been channel coded by the turbocoder. In LTE, you can actually have two code words in parallel that can independently be channel coded and then transmitted in parallel in case of the spatial multiplexing scheme. After scrambling and modulation of the code words, the MIMO layer mapping and precoding takes place. And that is the stage where it's actually decided whether transmit diversity or spatial multiplexing is applied, and which would result then in a different mapping and precoding operation specific to each MIMO mode. And also a wide range of configuration options exists at this stage. You have different precoding types depending on the radio channel characteristics, for example. Then the resulting signal out of the MIMO precoder is mapped on the OFDM time frequency resources for transmission on each antenna port. And again, LTE supports up to 4 transmit antennas at the base stations. Could also be 2, for example, depending on whether it's 2x2 or 4x2 or 4x4 MIMO. So now to better understand this layer mapping and precoding stage from the slide before, let's have a closer look on what happens in case of transmit diversity. So what is really done in these stages there of the signal processing. And the example shown here is for a 2 transmit antenna case. And it shows the space frequency block coding. So in case of transmit diversity, only one code word can be transmitted at once because we do not have spatial multiplexing. And the figure illustrates what happens to 2 symbols, D0 and D1, of that code word. First of all, these symbols are split onto 2 different layers in the layer mapper, and they are then pre-coded according to the space frequency block coding scheme, which is predefined in the standards. So the example shown here shows that the symbols are duplicated and then the conjugate complex signals, or even the negative ones, are transmitted according to a predefined rule. The resource element mapper defines how to transmit these symbols in time and frequency and over the antennas. And it's shown here that the same information is transmitted actually on both antennas because we have transmit diversity, but with different precoding. So antenna 1 in this example, TX1, transmits the symbol D0 at a certain subcarriers. At the same time, the antenna 2 transmits the symbol D1 on this subcarrier, with a special coding applied for this symbol. And looking at this other subcarrier, it's vice versa. TX2 transmits D0 and TX1 transmits D1. So actually we transmit a redundancy of information, but we achieve an increased robustness, but no increase in throughput or data rate compared to the single antenna case. So this is transmit diversity. Now let's have a look at the downlink spatial multiplexing operation in LTE, which again uses a codebook-based precoding. So what is a codebook? The codebook is actually for the 2x2 MIMO case shown here on the left-hand side, this table taken from the specification. The table effectively contains entries of precoding vectors and matrices, which are multiplied with the signal in the precoding stage of the base station. So now the selection which of these matrices or vectors to take, which codebook entry to select, is taken in the base station, and the decision is based on the regularly received UE feedback that the UE is providing. So the UE is of course estimating the radio channel and also evaluating the quality of the received signal, and based on that the UE recommends the optimum precoding matrix out of the codebook. The codebook is known of course at the base station and the UE side. And this feedback is called precoding matrix indicator, PMI, so the UE is actually pointing to one of these entries. And how is that done? So the UE is actually evaluating which precoding matrix would maximize the reception quality. Besides the PMI, the UE also reports CQI feedback, channel quality indication, and also a rank indication, RI, which provides information on the rank of the channel matrix. So that information will provide the base station with input whether spatial multiplexing or transmit diversity should be used. So this is downlink spatial multiplexing based on the codebook-based precoding as the other possible MIMO mode, and the base station has now the different configuration options available here. Finally, we look at the LTE uplink. There's no single user spatial multiplexing defined for the LTE uplink as we have seen for the downlink, and this is caused by the fact that the UE is not supposed to have two full RF transmit chains. But still the UE may have two transmit antennas and can switch the RF path between either one of them to exploit the diversity effect due to that. So the base station provides feedback to the UE which transmit antenna to use, and this is a closed loop scheme as well, so the scheme is optional for the UE to support. That's important to note, not all UEs have to support this. Another scheme used in the uplink is the so-called multi-user MIMO or collaborative MIMO, supported in LTE, so two UEs actually transmit simultaneously over the same time frequency resources that is indicated in this small picture, and the UEs are actually scheduled by the base station, so the base station needs to decide whether this is actually possible or not, and each UE just needs to have one transmit antenna in this case, as it's also indicated in this picture. But you can imagine that this scheme only works in certain radio conditions, so it's really up to the base station to evaluate that carefully. Multi-user MIMO enhances the capacity, as you can imagine, because you exploit the radio resource twice by sending different UEs over these radio resources, and the users share the same radio resources. So the base station has to distinguish the users again, and that is done by different reference signals that are assigned for the different UEs.